So, we move on to the next chapter, which is on phase transformations. In the truest sense, this itself is an entire course by itself, but here we will consider some of the salient and important features of phase transformations. Especially we will talk about the phenomena of nucleation and growth. We will talk about two kinds of diagrams, which are the TTT and CCT diagrams, which are invaluable tools for a material scientist. Then we will talk about certain applications of phase transformations in transformation of steel and certain other phenomena. The book by Porter and Easterling is a standard text for this subject and has served the materials community for quite some time as an important resource for phase transformations. Before we start this chapter, let us do a very simple experiment, an experiment which you would have seen many times before, but let us try to understand it from a different perspective, from the perspective of phase transformations. So, to do the simple experiment, I have here with me an aerated drink here, and so I have a glass here, and what I am trying to do is, of course, I am trying to take this aerated drink and so zoom out kar lijiye. So, and I just fill this aerated drink into this bottle. When I opened the bottle, there was some sound and the gas escaped, a little bit of the gas. But now what I am doing, I am taking this aerated drink and let me assume that I am pouring this into the glass. I observe something that slowly bubbles evolve. You can see that if you observe the glass closely, slowly bubbles are evolving, and the gas which was dissolved in this aerated drink is slowly evolving out. This gas was originally put into this aerated drink at high pressures, and now when this liquid which has dissolved gas in it is exposed to atmospheric pressure, which is lower than the pressure at which the gas was incorporated, and this gas is of course carbon dioxide. Now I see that the bubbles are slowly evolving. Further, what I will try to do is that, and if somebody observes carefully, some of these bubbles tend to form on the walls of the glass. They do not form uniformly all over, but they preferentially form along the walls of the glass. A similar phenomena you would have noticed when you say, for instance, pour wine or beer into a glass, wherein you would observe that these bubbles tend to form at some points preferentially, especially at the liquid glass interface. Now I have salt here with me, and suppose I take a pinch of this common salt and put it into this liquid, you can observe what happens. You see there is vigorous bubbling taking place, and if I had this, you can see even now that there is bubbling going on, and if I had this glass full of this liquid, in fact this liquid will tend to pour over if I put this salt into it. So you can clearly see that my putting salt into it has somehow invigorated the process of the evolution of bubbles. In other words, by putting salt, I am able to evolve more gas. That means now this liquid will tend to come down to its equilibrium concentration of the dissolved gas. So this is an important, simple but important experiment in understanding the phenomena of phase transformations. So number one, we observe that the gas was put into this aerated drink at a higher pressure. When I brought this to atmospheric pressure, this liquid, by pouring it into a glass here, at one instant all the gas does not escape. This is surprising because at atmospheric pressure the solubility of carbon dioxide in this liquid is much lower, therefore the excess carbon dioxide should evolve and come out, but that does not happen. It starts to happen at a slow rate, typically by bubbles nucleating along the walls of the glass at the liquid glass interface. But by putting salt, which I did before, you can see that suddenly this process is invigorated, and you have, again you can see that the process the more bubbles tend to form when I put more of salt into it, and gas is evolved at a brisker pace, and therefore the solution tends towards its equilibrium concentration of carbon dioxide at atmospheric pressure, and that is an important point to note. So I have an experiment in which I have a high pressure gas put into a liquid, and then I have an under pressurization when I open this liquid and put it into atmospheric pressure, and further I see that this bubble evolution can be enhanced by putting a medium like salt. So let us return to the main chapter, and we will keep this experiment in mind, and we will try to return to it at an appropriate point to understand the phenomena involved as to why that the gas does not escape immediately on opening all the gas does not escape on opening the container, and it slowly evolves with time, and how does the salt help in this process of gas evolution. So, let us start with a overview of phase transformations. When one phase transforms to the other, we call it a phase transformation. Often the phase transformation is used to describe transformations wherein there is no change in composition, and we will take up a few examples of these also in the coming slides. That means phase transformation is a superset, phase transition is a subset of these phase transformations wherein there is no change in the composition and one phase transforms to the other. For example, suppose I have a paramagnetic phase of or a ferromagnetic phase of iron, and I heat this iron, it turns into a paramagnetic phase, and in this process there is no change in the composition. Suppose I am talking about a liquid, a pure iron in its molten form, and I cool this will transform into a solid iron, typically a polycrystalline iron, and this does not involve any change in compositions. So, such kind of phase transformations are also referred to as phase transitions. And we have already noted that when you are talking about phases, the phases can be defined either based on the geometry or a physical property, and similarly the phase transformation could be about based on the structure, in which case for example I have a cubic to tetragonal phase transformation, or it could be based on a property like the one I just considered, which is ferromagnetic to paramagnetic phase. In other words, a broad classification of phase transformations could be based on if the phase transformation involves a change in structure, does it involve a change in property, and of course I could always have a combination of both. That means I could have a transformation in which I have a change in the property that means I have a change in the property and a change in the structure. Like for instance, in tin, the white form of tin and the grey form of tin not only are structurally different, but their bonding itself is different, and therefore, the property changes when I have this transformation. And further we could have other classifications of phase transformations, and this could be based on kinetic aspects or it could be based on thermodynamic aspects. In this chapter of course, we will only consider a brief overview of some of these aspects, and we will leave the reader to more advanced courses on phase transformations to delve deeper into some of these concepts. Based on kinetic aspects, which essentially means I am talking about mass transport, phase transformations can be called diffusional or diffusionless transformations. Our essential focus in this chapter will be on diffusional transformations, though we will consider a little bit of diffusionless transformations as well. Based on thermodynamic aspects, we can classify phase transformations using a term called the order of a transformation, and we can classify phase transformations as first order, second order or higher order transformations. And often even subtler aspects of transformations come under the purview of phase transformations, though strictly speaking these are not phase transformation, but they are transformations of a subtler kind. Like for instance, we can talk about roughening transition of surfaces, coherent to semi-coherent transition of interfaces, etc. Like suppose I take a aluminum copper system, which we will consider later in this chapter, and I start heating this system. First of all I take it to high temperatures, solutionize, that means all the copper is present in the form of a solid solution in aluminum. Then I quench this solid solution to retain a solid solution, a super saturated solid solution at room temperature. Then I slowly heat it to a low temperature. Then I would see that initially I will form coherent precipitates, which on growth will become semi-coherent, and then finally they will become incoherent. These kind of interface change characteristics can also be brought into the purview of transformations, though that is of a subtler kind. Therefore, to review this slide, you have a broad subject of phase transformations, and of course, I will make a comment here that we will go to even a superset of this of phase transformations, and that will be in one of the coming slides. And a subset of these phase transformation is something known as phase transitions, where there is no change in composition involved. I could be defining a phase transformation based on a structure like cubic to tetragonal phase, a property like a ferroelectric to a paraelectric phase, or a combination of these. I could classify my phase transformations based on kinetic aspects or thermodynamic aspects. So, this slide brings out some of these in a pictorial form, that based on mass transport I can classify phase transformation as diffusional, and when I mean diffusional I am typically talking about long range mass transport, or diffusionless. For instance, we will consider in this chapter a particular kind of diffusionless transformation known as the Martensitic transformation. Further, thermodynamically, based on order, we can classify phase transformations as first order, which involves a concept known as nucleation and growth. We will dwell into this concept of nucleation and growth in a lot of detail in the context of transformations like solidification and alpha to beta phase transformations, etc. And typically, you can also classify based on order phase transformations to be second order or even higher order. Typically, second and higher order transformations are clubbed together, though in principle you could talk about second order, third order, etc. And as I pointed out, if a first order phase transformation involves nucleation and growth, a second and higher order transformation, the entire volume transforms simultaneously, and this is a characteristic, and an example of this could be the order disorder transformation. So, if, as I pointed out, even phase transformations in some sense is a restricted or a subset of, is a set of some superset which can be defined, which we will consider in this slide, of transformations of materials. Phase transformations are associated with change in one or more properties. Often this is the reason that we are studying phase transformation, that we want to engineer the properties. And if you, therefore, microstructure dependent properties we would additionally like to think about, and we would also worry as to how the defect structure and the stress state change apart from the phases. In other words, I need not only worry about the phase transformation, but I have to worry about how the defect structure changes and how the stress state in the material changes. When in an earlier chapter we had considered that residual surface stresses in glass toughens the glass, and similarly, suppose I want to harden aluminum, I can cold work the aluminum so that my defect structure, that means my dislocation density increases and therefore the material becomes hard. But suppose now I anneal this aluminum, it will lose its hardness because much of this dislocations would be annihilated, and therefore I would have a lower hardness or a lower strength. Therefore, from a property perspective, when I am talking about transformations in materials, I need to worry about the defect structure, the stress state, and also the phases and their distribution, and this implies that I have to deal with a broader subject known as microstructural transformations, because we have defined microstructure functionally to be phases, defects, residual stress and their distributions. Therefore, in a diagrammatic form, let us consider that phases can transform, and this we call phase transformation. We can have defects, defect structures can change, that implies, that means I told you the dislocation density can change, the vacancy concentration can change, we could have more of twins being introduced by deformation and which can get annealed, and therefore, I can have, apart from phase transformation, I can additionally have what we call a defect structure transformation. And the third component of microstructure, the residual stress, and therefore the stress state can be altered, and this stress state could be thermal residual stresses, or it could even be residual stresses coming from defects like dislocations, and therefore I can have a stress state transformations. And so, putting the picture together, I can have phase transformation, I can have defect structure transformation, and I can have stress state transformation, or in one phrase I can talk about, apart from phase giving rise to a microstructure, I can talk about a phase transformation going to a superset called the microstructural transformations. So, in this chapter, not only we will be talking about phase transformations, we will also briefly consider what we call microstructural transformations, and we will worry about treatments like annealing, we will worry about treatments like recrystallization, wherein the microstructure transforms. So, this is an important slide in which we have now used the concept of a microstructure and therefore evolved a superset to phase transformations, which is called the microstructural transformations. And at the end of this chapter, we would like to have the answers for some of these questions. Of course, some of these answers to some of the other questions some of these questions may be found in other places and other chapters, but we will try to understand some of these, try to search for some of the answers for some of these questions. For the first question, of course, is that we have what is a phase and what kind of phases exist. We have already dealt with it in the previous chapter, but we will again revisit this concept. Then of course, I will ask a question that what constitutes a transformation, and how can we cause a phase transformation to take place. That means, can I heat the substance, can I put it in a magnetic field, or can I pressurize the system? And we have already seen when we drew the iron pressure temperature unitary diagram that both pressure and temperature can cause phase transformation. But additionally, we have to note that other factors like electric fields and magnetic fields can also transformation, though we will not consider these aspects in detail here. Of course, again we will ask the question that what kind of phase transformations are there that we need to consider, and why does a phase transformation take place? That means, what is the energy considerations on the system that causes phase transformation to take place, and are there any barriers to this phase transformation? What is the relevant thermodynamic potentials which we need to consider? And we have already noted that if you are working at constant temperature and pressure, it is the Gibbs free energy which is the relevant thermodynamic potential which we need to consider when we are talking about phase transformations. That means that systems will tend to go downhill in Gibbs free energy, and therefore, if there is a lowering of Gibbs free energy possible by a phase transformation, then the system will transform. But however, we have to remember that Gibbs free energy can only tell us that if there is a tendency for a phase transformation to occur, it is the kinetics which will tell us that if actually the phase transformation will take place. In other words, thermodynamics may warrant, but kinetics may prohibit. And a classic example given is the window pane glass, for instance, which is present in many places in this room, that the window pane glass is a metastable state, and by crystallization the Gibbs free energy of that can reduce, but the kinetics is so frozen at room temperature that this glass can exist for a few hundred years without much change in its crystallization. And we need to worry a little bit before we understand some of the aspects of this chapter, and one of those important aspects is that we need to revise the concept of a surface, the concept of an interface, and the concepts of surface tension and surface energy. And we will do that very soon, but before that we will ask the questions that suppose I have a volume of material V, like for instance in the diagram below I have here a region which is marked in green, which is I will shade now. So, this region is, suppose I consider a volume of material V which is transforming, then what is the change in the energies I need to talk about? Of course, if I am assuming that this volume wants to transform, that means at constant temperature and pressure the Gibbs free energy must reduce. But when this uniform phase which was present suddenly threw out this little volume of green material, that means originally I had a matrix which is shaded in blue here. So, this is my matrix, and in this uniform matrix I suddenly have now a green phase. This implies that an interface has been created which is marked in red between the matrix and the new phase, which I can call for instance a second phase, and therefore, there is an increase in the interfacial energy. That automatically brings us to the point I just mentioned, that I need to understand what is this interface energy, what is the origin of this interface energy, and of course, one of the interfaces which is easiest to understand is the free surface. So, I can equivalently try to understand that what is the free surface and what is the origin of the surface energy, and how is this surface energy linked to the equivalent concept or a related concept known as surface tension. And if I am talking about a solid to solid phase transformation, then additionally I need to worry about what is called an increase in the strain energy. Okay. Now, to understand these aspects, let us draw this diagram once more schematically on the board. So, I have an uniform volume of material which I can call a matrix, and in this volume of a material suddenly I assume that there is a second phase present. Suppose this second phase is a blue phase. By the appearance of this blue phase, two things have happened. Number one, I would assume that the volume or the Gibbs free energy of a localized region is reducing because of the presence of this blue phase, which I will again once more highlight in yellow color. So, this is my phase which has been created. Okay. But and this implies two things. First of all, of course, I told you the first thing, the Gibbs free energy would be reduced corresponding to the volume of material created, but additionally an interface is created between the two phases. Suppose I am talking about a matrix M here, in which this phase is coming out, this blue phase, which I can call the beta phase, and this matrix I can call the alpha phase, then I have an increase in interfacial energy because of the presence of this. One additional term comes because suppose I am in this case, suppose this I am talking about not a solid to solid phase transformation, suppose I am talking about a liquid to solid phase transformation. That means I have a liquid bath in which I have the formation of a second phase, a solid phase. Then this solid phase, assuming it is a crystal, will have a lower volume with respect to originally the volume occupied by this liquid there. But then since I am working at constant temperature and pressure, and the volume is left free to expand or contract, therefore, there will be no strain energy associated with this system because of the formation of this little amount of solid, a crystal. So, this is my liquid. But suppose I am talking about a solid to solid phase transformation. So, this is a solid alpha in which a beta phase is coming. I would have an additional term which is the strain energy term. And we will try to understand all these energies in little more detail as we go along. So, the energy involved in general are the Gibbs free energy reduction, which is actually what is driving the phase transformation, an increase in interfacial energy which tends to oppose your phase transformation, and an increase in strain energy which becomes important in solid to solid phase transformation. In other words, if I am talking about a constant pressure system and I am talking about a liquid to solid phase transformation, usually the strain energy term can be neglected. And this is because, as we know, liquid can flow and accommodate the volume and shape change involved in a phase transformation. But on the other hand, if you are talking about a solid to solid phase transformation or even a formation of a liquid pocket within a solid, then often this may lead to certain strain in the material, and therefore, in a solid to solid phase transformation, I cannot ignore the strain energy term. So, let us try to understand the strain energy term before we go on to understand the interfacial energy term. Typically, we can understand the strain energy term by considering what is known as the Eshelby construction. And of course, I have to note that in general, if I am talking about a phase transformation, the product phase may have a different volume and a different shape as compared to the original matrix phase, and therefore, both dilatational and shear strains may be involved in a phase transformation. So, therefore, if I am talking about a phase transformation, I can write down So, I have two kinds of strains involved, the dilatational strains and the shear strains, and both of these dilatational and shear strains can give rise to corresponding strain energy which is stored in the material. And to understand this, as I pointed out, I will do what is known as the Eshelby construction. So, let us consider the figure here below, in which there is a blue matrix phase in which a volume V of material is ready to transform. Of course, we already seen that we need some kind of a thermodynamic stimuli for this transformation to take place. Example, we could have, for instance, cooled this, for instance, suppose I am talking about a alpha phase transforming into a beta phase or a gamma phase transforming into an alpha phase, I could have cooled the system down below the transformation temperature. Like for instance, I could be talking about the high temperature form of iron, which is gamma, and I am cool the system below its transformation temperature, and therefore, it wants to transform to the alpha phase. But this volume V of material, assuming that it is ready to transform. What I do a mental construct in which I take this material of volume V out, allow it to transform outside, and then I try to insert back this material after transformation into this original hole which was created. So, I have this hole has a volume V, because now I have just pulled out this volume V of material out of this matrix. Now, what happens if I pull this out and allow the transformation to take place? In general, of course, I could have only a volume change as shown below. That means, the volume after transformation could of course be larger or smaller. In this schematic, we have shown a larger volume here, or this transformation could involve a change in shape, in which case of course, this volume of material would become changed in shape. So, suppose I just have a shear strain involved, then this would be the new shape of this transformed volume. So, I could have a new shape, but in general I could have a change in both shape and volume. Since this aspect is important, I will just go to the board and draw this all over again. So, I have a volume V of material which I have plugged out from the material, from the inside of the matrix. I can have this volume V of material transforming just by pure shape change. That means, I assume that the volume is constant. I could have a pure volume increase, that means, the shape is same. Or I could have a combination wherein I have a volume change and a shape change. So, I have volume V of material and it is changing in shape. For instance, in this case, in the schematic it is a square which became a rhombus, or I could have a volume change, in which case for instance, I have considered a bigger volume here, but in principle it could also be a smaller volume, or I could have a transformation in which I have a change both in the volume and the shape of the material. So, I have in general a possibility that when the phase transformation takes place, because for instance, this could involve for instance, a change in crystal system itself, and which means that the system could go from a cubic phase for instance to a monoclinic phase, which could involve a change both in the shape and the volume of the material. And the next important step in this whole construction, the Eshelby construction, is the fact that this volume of material is not standing free. Here of course, I plugged this volume out of from the solid. Suppose I had originally had a solid like this, and I took a volume V of material, plugged it out from the solid and then put it here, and I considered the transformation. And this transformation can be thought of as having something known as stress free strains . And this term stress free strains needs to be understood a little more. Suppose I had a metallic body and I pull it, that means that I am applying some force on the material, which translates into stress inside the body, and this stress leads to elongation, which means strain. Therefore, I have stress coupled with strain, but in certain situations, like in the example of phase transformations, I could have something known as stress free strains, and in certain other situations I could have strain free stresses. So, let us take examples of these. What is stress free strain and what is strain free stresses? Suppose I take two rigid walls and I put a body between the two. So, this is my rigid walls and have a body between the two, and this body I will just label in red. So, this is my red body which is kept between the walls. In an alternate scenario, I will just take a freestanding body here of the same volume. So, this is my freestanding body. I will heat both these configurations. So, this is this is configuration 1 and this configuration 2, I heat both the systems. Because of thermal or the heating, this body will expand. but in the expanded state there will be strains, that means the body would have become longer. Schematically I am showing it this way, and of course it would have increased in volume as well. So this body would be expanded. Suppose I am interested in this direction, x direction, so it would have become longer in the x direction, but there will be no stresses in the material. That means there are strains, but there are no stresses. So this is what we call stress free strains. Similarly, I took this volume of material V, a freestanding body, and allowed it to transform. There are strains, there are shear strains and there are dilatational strains, but there are no stresses. Therefore, these thermal stresses are akin to this phase transformation. Thermal strains are like phase transformation strains which are stress free, and this of course is true for a freestanding body which is heated. On the other hand, suppose I have a body which is between two rigid walls and I heat it. In this case, these rigid walls will not allow the body to expand. That means the strains will be 0. But because I am heating the body will develop stresses. Okay. So these can be thought of as the opposite of stress free strains, which means these are strain free stresses. So these are strain free stresses, and I have to remember the strain I am talking about is the net strain, which is a combination of the original strain it wants to expand counteracted by the rigid walls which is stopping it. So I can have stress free strains and strain free stresses, and the one which is relevant to our construction now is the stress free strains, which can easily be understood by taking an analogy of a freestanding body which is heated. So now the next step is that I have now with me a body which is this, which has changed. Say for instance, now for simplify matters further, I will assume that it has just changed in volume. So it has become bigger, though the generality will not be lost if I consider shape change also, but I consider a body which is bigger in volume now. Now this volume of material has to be inserted back into this original volume which was taken from where it was taken out, because now actually this is not standing free, this is actually a part of the continuum wherein I have this matrix and this volume V, and therefore I have to make a mental construct in which this volume V is inserted back into this. So in the process of doing so, let us see what happens. Let us go back to the slide. So what I am doing here is that I have this volume V prime which is now of the transformed material, and I take this volume V prime and try to put it back into the original black hole which was created when I took out this material. So what would then be the tendency? That since this volume is larger, as I have considered, just in shape, just in size, then this volume of material will tend to push the matrix outward, that means this, and the matrix will try to push this material inward, because the matrix is not made of a zero modulus material, it will also tend to push this whatever the transformed material back, and therefore I will land up with an equilibrium configuration which is shown by the dotted line. So the volume that the precipitate will occupy will not be the original volume which was created as I showed in the board, that means the larger volume there. It will not be the volume of the hole which was created, it will be something between the transformed free volume or the transformed volume under free boundary conditions vis-a-vis the original hole which was created. So I will have an equilibrium shape which is finally the one which is marked in head, and obviously the whole process involves strains, the final net process, and therefore there will be strain energy associated with this whole process. And if I look at the stress state, I will notice that the precipitate will be under compression, but the matrix will be under tension, because if this is overall a freestanding body, then the net stress state has to be 0. Therefore, all this strain energy which the system is paying will have to come from somewhere, the reduction in the Gibbs free energy which was originally present. In the absence of this strain energy, I would assume that the transformation can take place much more easily, but now because there is a strain energy term involved, the energy cost to the system is larger, and therefore the system has to pay a higher price now, not only in terms of the interfacial energy which is interface energy which is created, but also in terms of the strain energy which is coming from the phase transformation. So therefore, to summarize this slide, I can understand that strain energy can play an important role in solid to solid phase transformations. This strain energy, the origin of this strain energy can be understood by what we call the Eshelby construction, wherein we take a volume of material, pluck out a little portion of it, allow it to transform, reinsert it into the original hole which was there, allow the system to equilibrate, and in the process understand the stress state of the system and the strain energy which comes from the transformation. And these two terms, as we have noted, the interfacial energy and the strain energy, oppose our phase transformation, while it is the Gibbs free energy of the volume which is transforming, which is helping the process of the phase transformation. Now, before we consider some examples of how this phase transformation can take place, and we will consider here detail of the first order phase transformations, we need to understand this other term which we had considered, which is the interfacial energy. The origin of this interfacial energy, what do we exactly mean by the interfacial energy, and that will be the next thing we have to consider. To understand the concept of interface energy, we will use the concept of surface energy because it is somewhat easier to understand, and to understand surface energy we will consider a small anecdotal story. Person A meets person K and asks person K, why are you looking so glum today? Person K says, I suffered a loss of 4 crores of rupees in my business this year, that is why I am not looking very cheerful today. Then he asks, how did you suffer a loss of 4 crore rupees this year? What went wrong with your business? He says, last year I had a profit of 16 crore rupees and this year I have a profit of only 12 crore rupees, which means that I have suffered a loss of 4 crore rupees. So, the question to ask of course from this story is that, did person K really suffer a loss of 4 crore rupees? Because at the end he still had a profit of 12 crore. It was just 4 crore with respect to the last year's profits, which was 16 crores. Similarly, we have to ask ourselves this important question. Of course, the story is here to tell you the connection between this and the surface energy, and that will become clear as we discuss more. The question we have to ask ourselves, is surface energy, or for that matter interface energy, truly an energy, and if at all yes, in what sense can we consider it to be an energy? To understand these concepts, let us consider a collection of atoms which are far apart. That means they are non-interacting and therefore they are not bonded to each other. Now, suppose I do a mental construct in which all these atoms are brought together and say I form a crystalline array. And since originally I talk about this original state as some 0 state in energy, I can draw that 0 state in energy, and on formation of a crystalline state I assume that there is bonding between the atoms. That means I assume, suppose there are n atoms in this assemblage, and then I assume that each one of those atoms is bonded to its neighbors. So, assume that in this crystalline array, say I take an atom here, this atom is bonded to all its neighbors. Suppose the bond energy reduction per bond is EB, that means then given that EB is the bond energy reduction per bond, I can calculate the total reduction in or energy reduction in energy when I form this crystalline array as because each atom is bonded to 4 atoms, I have total energy reduction. Suppose I call this total energy reduction ET is equal to 4 times into EB into the number of atoms in this assemblage. Say for instance that number is n, the total number. But anybody who sees this experiment, that means now I have taken a non-interacting set of atoms whose energy state in this energy axis is 0, then I make a crystalline array out of this assemblage of atoms, and in this crystalline array now the reason for formation of the crystalline array is that each atom can lower its energy by forming bonds. These bonds are shown in red color, and because of this formation of bonds, each atom's reduction per bond is EB. That means if it is bonded to 4 neighbors, then I have a reduction of 4 EB per atom, and since there are total n atoms in this system, I will have a total reduction in energy as 4 EB into n. Anybody clearly watching my calculation can point out the error, that actually the surface atoms which are here are clearly not bonded to 4 other neighbors, they are just bonded to 3 other neighbors, 1, 2 and 3. So, there are 3 bonds, 1, 2 and 3, and therefore, and suppose this is an infinite array, and now that means it is infinite in this direction, it is infinite in this direction, infinite in this direction, but this is my surface. Therefore, I will shade all the surface atoms. So, this can be called a semi-infinite crystal. In the semi-infinite crystal, some of the atoms are sitting on the surface, and these atoms do not saturate their bonds. That means, there are some unsaturated bonds, which I will show by dotted lines. So, these surface atoms are only bonded to 3 other atoms, that means, they have not lowered their energy as much as I calculated. So, what is this lowering of energy? Is that I come to a new state. So, this is state 1 for instance, I come to state 2 here, which is now the crystalline state, and now this is my ET, which is negative, because it is lowering in energy because of the crystal formation. But as you can clearly see, I have overcounted the bonds, the number of bonds. The surface atoms are not as well bonded as the interior atoms, and therefore, I have to correct for the surface atoms, and suppose this is the number of surface atoms is n surface, I have to correct for this surface energy, and the net energy of the final system would be this E So, this will be step 3. In step 3, I am correcting. So, this is my step 1 here, my step 1 of course, I start with here. The step 2 is my crystalline state, wherein I did an overcounting of the bonds, and to correct for the fact that there are some surface atoms, and therefore, I have to correct for the fact that these surface atoms Ns are actually bonded only to 3 other neighbors, and of course, I have to account for the fact that there is a bond energy per bond of Eb, and of course, this is a crude what we call broken bond kind of a calculation. In reality, things are much more complicated, but this is a nice illustrative example, and therefore, I have to correct and land up in state 3, wherein the true surface has been taken into account. That means, we are not talking about an infinite crystal, but a semi-infinite crystal, wherein there is one surface. Of course, if it is bounded by many more surfaces, it is a finite crystal, then I have to correct for all the surfaces. But the important thing to note is that this is what is my surface energy. This correction I am doing is called the surface energy. So, this is the origin of surface energy. In other words, surface energy is not with respect to the 0 state, the unbonded state or the non-interacting state, but the reference state for the surface energy is the fully bonded crystalline state, which is the state 2. It is actually the correction you make to the error of overcounting an atom, all the atoms being bonded as if it is a full crystalline state. So, this is my surface energy, and as I pointed out, in spite of the presence of the surface, if you look at the overall system, there could be a reduction in the energy as you go from the unbonded state to the state with the surface. So, there is this reduction energy still possible. In other words, the system with even a surface might have a lower energy as compared to the free state. So, this correction is what is we call surface energy, and in some sense, because its reference state is the fully crystalline, fully bonded state, it is a correction term and not an energy in itself in the sense of starting with a non-interacting collection of atoms. So, it is interesting to note this surface energy, as I said, is a loss not with respect to the non-interacting state. It is not truly a loss, it is a loss because of the fact that you overcorrected the atoms. Of course, this calculation could have been performed in a different way. I could start with a non-interacting set of atoms, then I could find out the number of atoms which are sitting on the surface and call that Ns, and I know that these Ns atoms are bonded to 3. So, I will write down as 3 EB. So, I will get a step 1 reduction E1, then I will locate the number of bulk atoms and I will write it as N bulk, and I know that these bulk atoms are bonded to 4 bonds. Therefore, I will write my energy as E2, and therefore, in 2 steps I can arrive at the final state, which is the state 3. That means that I consider my bulk atoms separate from the surface atoms. I do not start from 1 and land up in 2, but I land up at step 3 in 2 stages. That means, I first lower for my surface atoms, which is a little small lowering E1, then I lower for my bulk atoms, and finally land up in the final state, which is this state which I am interested in. So, in 2 stages I can lower, and in this case of course, the mystery of the surface energy would vanish. So, this is something which we need to understand, but this illustration should not confuse you, because this illustration is meant to truly understand the origin of surface energy, but as we shall see, the effects of this surface energy is very real, because the surface atoms now are in comparison to the bulk atoms are poorly bonded. They will always want to lower the surface area, and that means atoms on the surface will want to go towards each other, and this will automatically result in surface tension, because now if I put out more atoms on the surface, that means that suppose I am talking about a liquid and there are more atoms on the surface, I am going to pay a higher price for these atoms which are not that well bonded. Therefore, the surface will want to close in on itself, and therefore, this will result in real effects like surface tension. And there are many more interesting phenomena which are related to the surface tension and surface energy, and its role here in phase transformations definitely is of important consequence. So, we have tried to understand 3 terms contribute to the formation of for instance, a phase transformation. One is the Gibbs free energy, which helps you, the interfacial energy, which we just now understood, which tries to oppose you, because now similar to the surface, the interface atoms are poorly bonded with respect to either the solid, which is these inside solid, either the matrix or the, for instance, the precipitate. So, suppose I have a system here with a precipitate beta. Now, the atoms sitting on the interface here are poorly bonded with respect to the beta or even with respect to the alpha. So, they have a higher energy state with respect to both of those crystals we are talking about, and therefore, interfacial energy also has a similar origin in terms of poor bondedness, though we have to remember interface energy, there are material on both sides, unlike a surface where on one side we consider either vacuum or air at best. So, the third term is the strain energy, which we have understood in detail now. Now, to understand further phase transformations, let us take up the example of solidification of a pure metal. Though this is a simple and illustrative example, we will see that this can make us understand some of the important issues involved, and the most important of them being the issue of nucleation, and we will often find in literature terms like nucleation barrier. That means, it seems like nucleation is going to stop this phase transformation from taking place. So, we will understand these terms like nucleation barrier, undercooling, and also something known as homogeneous and heterogeneous nucleation.